This phenomenon has been observed many times in winter, when small birds take refuge in coal storage areas to take advantage of the heat produced by the coal and keep themselves warm. It may be difficult to believe how pieces of coal, simply piled on top of one another in a normal temperature environment, can spontaneously ignite. However, flammable materials such as solid fuels can reach their ignition point on their own as a result of increasing temperature caused by slow, exothermic chemical reactions. Coal, in its various forms, has a naturally porous structure. These pores contain large amounts of air, and the oxygen trapped within them reacts slowly but continuously with the coal in a series of exothermic reactions. This gradual reaction causes the temperature of the piled coal to rise over time. In large coal storage facilities, if this heat is not properly managed and dissipated through appropriate engineering methods, the temperature can continue to increase until the solid fuel reaches its ignition point. With ample air both within the pores and around the coal piles, this can lead to a fire or even an explosion in the storage area. One effective method to prevent such disasters is to crush the coal into smaller pieces. Reducing the size of the coal increases its surface area, which allows heat to transfer more efficiently to the surrounding air and helps prevent dangerous temperature buildup. Consider a flat slab of coal with a thickness much smaller than its other dimensions, such that heat transfer can be treated as one-dimensional. Within solid, oxygen reacts with coal through a set of exothermic reactions. We assume these reactions can be modeled as an effective first-order reaction, whose rate depends solely on the oxygen concentration. Because oxygen is plentiful in the external environment, its concentration at the coal surface, and therefore inside the porous coal, remains essentially constant. As a result, the reaction rate depends only on temperature. The reaction rate constant follows Arrhenius behavior, and the heat of reaction, activation energy, and pre-exponential factor are known. The thermal conductivity, specific heat, and density of the coal are taken as constant and temperature independent. Initially, the slab is at a uniform temperature and is exposed on all faces to ambient air at a known temperature. Heat exchange with the surroundings is characterized by a known convective heat transfer coefficient. To prevent spontaneous ignition, the characteristic dimension of the coal, its half thickness, must not exceed a certain value, known as the critical thickness. If the slab is too thick, internally generated heat from oxidation cannot be removed efficiently, causing the temperature to rise until thermal runaway occurs. The objective is to derive an expression for the critical thickness, expressed in terms of the kinetic and thermophysical parameters, and to compute that thickness. We begin by defining a coordinate system that uniquely specifies the position of every point within the domain. The coal sample is modeled as a flat slab whose thickness is much smaller than its length and width. For convenience, the x-axis is taken perpendicular to the slab surface, with x equals 0 located at the midplane. Although the slab thickness is exaggerated in the schematic representation, the aspect ratio justifies treating heat conduction as one-dimensional in the x direction. Consider a differential control volume of thickness delta x, located between x and x plus delta x, with cross-sectional area S, equal to the area through which heat is exchanged with the surroundings by convection. Heat enters and leaves the control volume by conduction. An energy balance is written for this control volume over a small time interval delta t, accounting for heat conduction and heat generation due to the exothermic oxidation reaction. The heat conducted into the control volume at position x during small time interval delta t, minus the heat conducted out at position x plus delta x, plus the heat generated internally by the chemical reaction within control volume during delta T, must equal the increase in internal energy, in this case enthalpy, of the material within that volume. The heat accumulated within the control volume results from the temperature variation over the time interval delta T, and can be determined using the mass of the coal, its specific heat capacity, and the corresponding change in temperature. Dividing the resulting balance equation by both delta X and delta T, substituting the constitutive relations for heat conduction and reaction kinetics, and taking the limit as both delta X and delta T approach zero, we obtain, via the definitions of the gradient and partial derivative, the partial differential equation governing the transient temperature distribution in the coal slab. The thermophysical properties, density, specific heat, thermal conductivity, are taken as constant and temperature independent. To solve this second-order partial differential equation, two boundary conditions in the x direction are required. Since both faces of the slab exchange heat with the ambient environment, each boundary condition is obtained by applying an energy balance at the surface. The conductive heat flux arriving at the surface must equal the convective heat removed by the surrounding air. Because the two sides of the slab are exposed to identical ambient conditions, the system exhibits central symmetry. Consequently, the temperature distribution within the coal slab is symmetric about its midplane, making the temperature an even function of the spatial coordinate. In this situation, because the function is even, the derivative of the temperature with respect to x at the center is zero. As a result, the differential equation can be formulated over only half the slab's thickness, with a symmetry boundary condition at the center. Physically, this is equivalent to considering a slab of half the original thickness, with one side perfectly insulated and the other side exposed to the surrounding air. The temperature distribution in this simplified model is identical to that in the actual slab. In addition, an initial condition specifying the temperature distribution at T equals 0 is required to ensure that the mathematical problem is well posed. That is, a solution exists, the solution is unique, and it depends continuously on the initial data. We next non-dimensionalize the governing equations by introducing appropriate dimensionless variables. We begin by applying the chain rule to express the time derivative of the temperature in terms of the non-dimensional temperature. Similarly, the spatial derivative of temperature with respect to x is rewritten using the dimensionless coordinate, and the second derivative is obtained by differentiating once more. Using these relations, the governing PDE, along with its boundary and initial conditions, is rewritten in fully non-dimensional form. This transformation simplifies the mathematical analysis and highlights the key dimensionless parameters governing the heat transfer process. The non-dimensional formulation introduces dimensionless groups, the Biot number, the gamma parameter, related to the activation energy of the chemical reaction, and the beta parameter, which compares the internally generated heat to the heat conducted away. The Biot number represents the ratio of the internal thermal resistance of a solid to the external resistance associated with convective heat transfer from its surface to the surrounding fluid. It is a measure of how easily heat generated inside a material can be transported to the environment. If the material is a very good thermal conductor, it offers little resistance to the movement of heat from its interior to its surface. Under such conditions, temperature differences within the solid remain very small, and the temperature field is nearly uniform at any given time. This behavior corresponds to a small Biot number, approaching 0, indicating that internal conduction is much more effective than external convection. At the surface, heat transfer to the fluid occurs through a thin thermal boundary layer that forms next to the solid. Within this layer lies essentially the entire resistance to convective heat transfer. Beyond it, the fluid is in a free-flow region with negligible temperature gradients. When the flow around the solid becomes more turbulent, mixing in the fluid increases, thinning the boundary layer and enhancing heat transfer. As a result, the convective heat transfer coefficient becomes large, and the temperature of the solid surface approaches the ambient fluid temperature. Under these highly convective conditions, the external resistance becomes very small, and thus the Biot number becomes large, reflecting that conduction inside the solid now limits the overall rate of heat removal. Because the governing partial differential equation is nonlinear, it does not admit a closed-form analytical solution. To proceed analytically, we introduce a simplifying approximation. The nonlinear reaction term is expanded in a first-order Taylor series around the ambient temperature. Under this approximation, the PDE becomes linear. The resulting equation is a linear partial differential equation with homogeneous boundary conditions, posed on a finite interval. However, we cannot immediately apply the method of separation of variables, because this method requires that the differential equation itself be homogeneous. In our case, the PDE still contains an inhomogeneous term. We therefore modify the problem so that separation of variables becomes applicable. To do this, we express the solution to the differential equation as the sum of two functions. One is the steady-state solution, that is, the solution that eventually stabilizes within the slab of coal over time and is independent of time. The second is the transient solution, which decays with time and eventually vanishes. Substituting this form into the PDE and applying the boundary and initial conditions, since the steady-state dimensionless temperature does not vary with time, it satisfies the inhomogeneous second-order ordinary differential equation obtained by setting the time derivative equal to 0. The full problem naturally decomposes into a steady-state, inhomogeneous, ODE with homogeneous boundary conditions, and a homogeneous PDE with homogeneous boundary conditions whose initial condition depends on the steady-state solution. The steady-state equation is a linear, second-order ordinary differential equation and contains a constant inhomogeneous term. For convenience in the calculations, we introduce the parameter delta, which is defined in terms of the dimensionless parameters beta and gamma. Its solution consists of the sum of a complementary solution, obtained by solving the associated equation without the inhomogeneous term, and a particular solution, which must be a constant because the inhomogeneous term is constant. The complementary solution is a linear combination of sine and cosine functions. The particular solution is obtained by substituting a constant into the differential equation. Thus, the general steady-state solution is the sum of these two components. The constants A and B in the homogeneous part are determined using the boundary conditions. From the symmetry condition at the center of the slab, we know the steady-state solution must be an even function. This requires the coefficient of the sine term to be 0. Applying the convective boundary condition at the outer surface determines the coefficient of the cosine term. With these constants determined, the complete steady-state temperature distribution is obtained. This solution describes the temperature profile in the slab after a sufficiently long time, when transients have died out and the system has reached thermal equilibrium. Once the steady-state solution has been determined, the initial condition for the transient solution is fully specified. At this point, the transient partial differential equation can be solved using the separation of variables method. This is now possible because the transient equation is linear, homogeneous, defined on a finite spatial interval, that is, it is a boundary value problem, and also subject to homogeneous boundary conditions. All of these requirements must be satisfied in order for the separation of variables technique to be applicable. If even one condition fails, the method cannot be used. In the separation of variables approach, the solution is assumed to be the product of two separate non-zero functions. F depends only on the spatial coordinate and is at least twice differentiable, and G function depends only on time and is at least once differentiable. Substituting this product solution into the homogeneous transient PDE yields an expression involving the time derivative of G and the second derivative of F with respect to space. Dividing the resulting equation by the product of these two functions, which is non-zero, separates the variables. The left-hand side depends only on time variable, while the right-hand side depends only on z. Since a function of time cannot equal a function of space unless both sides are equal to the same constant, we conclude that each side must equal a real constant, commonly denoted by k. The real number k is called the separation constant. The separation of variables technique takes its name from the fact that it literally transforms the original transient PDE into two separate ordinary differential equations, one in space and one in time, which can then be solved individually. The two ordinary differential equations obtained through separation of variables may now be solved independently. We begin with the time-dependent equation. Its solution is straightforward. The function g is an exponential function, reflecting the decay of each transient mode with time. As mentioned earlier, the transient part of the solution must decay with time and eventually vanish. Therefore, it is expected that the exponential term in the solution will decrease over time, causing the temperature distribution in the slab to approach its steady state. This requirement imposes a constraint on the separation constant k. Specifically, real number k cannot be positive or zero, because a zero or positive value would cause the exponential term to grow rather than decay, contradicting the physical expectation of a diminishing transient response. To solve the spatial equation for f, we first rewrite it in standard form. The boundary conditions for f follow directly from those of the transient, homogeneous partial differential equation. Specifically, the mid-plane symmetry provides a zero flux, Newman, condition at z equals 0, while the convective heat transfer at the slab surface imposes a Robin boundary condition at z equals 1. Defining minus square root of k as a new constant, which is a positive real number, the second-order, constant coefficient ordinary differential equation has a general solution that is a linear combination of sine and cosine functions. The coefficients in this linear combination, denoted d and e, are determined using the boundary conditions. From the symmetry boundary condition at the center of the slab, we know the solution must be an even function of z. Therefore, the sine term must vanish, implying that d equals 0. Applying the convective boundary condition at the outer surface then produces an algebraic equation containing the remaining coefficient, because e cannot be 0. Otherwise, the solution would be identically 0, contradicting the original assumption. The resulting algebraic equation determines the permissible values of the separation constant k. This algebraic equation cannot be solved analytically in closed form. A graphical examination clearly shows infinitely many intersection points between the corresponding curves. Each intersection corresponds to a valid solution. Thus, the separation constant can take only those specific values that satisfy the boundary condition. These values are the eigenvalues of the spatial differential equation. These eigenvalues form an infinite, strictly increasing sequence of positive real numbers. All of them correspond to angles in the first and third quadrants of the trigonometric circle, where the tangent function is positive. As the Biot number increases, the eigenvalues approach the odd multiples of half pi. Each eigenvalue has a corresponding eigenfunction Fn, and each produces its own exponential time function Gn. Thus, every eigenvalue generates a valid transient mode that satisfies the differential equation and the boundary conditions. At this stage, however, no single eigenvalue can satisfy the initial condition of the PDE. This apparent contradiction is resolved by the superposition principle. Since all transient mode individually satisfy the homogeneous PDE and boundary conditions, any linear combination of them also satisfies the PDE and the boundary conditions. The coefficients n are real numbers. They are determined by imposing the initial condition and expanding the initial dimensionless temperature deviation, after subtracting the steady-state solution, into a Fourier series in terms of the eigenfunctions. The orthogonality of the eigenfunctions ensures that each coefficient can be obtained independently as a ratio of integrals. Evaluating these integrals requires use of the explicit steady-state temperature distribution, trigonometric identities, the relationship between the Biot number and the eigenvalues, and standard algebraic manipulations. Once the coefficients n are computed, the transient solution is completely determined. Adding the transient contribution to the previously obtained steady-state solution yields the full dimensionless temperature distribution. This expression provides the complete time evolution of the temperature distribution in the slab. The obtained analytical solution for the temperature distribution inside the slab of coal represents how temperature varies with both space and time due to the exothermic reaction occurring within the slab. This temperature field is written in dimensionless form as the sum of a steady-state component and a transient component. The solution of the dimensionless temperature contains exponential time-dependent terms. For the temperature inside the slab to remain bounded and to eventually approach the steady-state distribution, every one of these transient terms must decay to zero as time progresses. This requires that the exponential factors be negative, which occurs only if the parameter delta is smaller than all of the eigenvalues. Since the eigenvalues form a strictly increasing sequence of positive real numbers, the most restrictive and therefore controlling condition is associated with the smallest eigenvalue. Thus, the necessary and sufficient condition for decay of every transient term, and hence for avoidance of thermal runaway or spontaneous ignition, is delta parameter must be less than the first eigenvalue. If instead delta exceeds the first eigenvalue, the exponential terms grow with time, the temperature increases without limit, and ignition occurs. The first eigenvalue depends on the Biot number, which characterizes external convective heat transfer. Increasing the Biot number corresponds to improving convective cooling, which pushes the eigenvalues upward. Larger eigenvalues make it easier to satisfy the stability condition, and therefore ignition becomes less likely. Conversely, when the Biot number is small, the eigenvalues decrease, making it easier for the reaction term to dominate and increasing the likelihood of ignition. Thus, the smallest eigenvalue, and therefore the critical value of the parameter delta, depends directly on both the slab thickness and the external convective heat transfer coefficient. At the critical state, which represents the transition between stable behavior and thermal runaway, the parameter delta is equal to the first eigenvalue. Combining the definition of delta, the definition of the dimensionless reaction parameter beta, the eigenvalue relation obtained from the boundary conditions and the expression for the Biot number, we obtain a system of 5 algebraic equations with 5 unknowns. By combining and simplifying these equations, one obtains a closed-form expression for the critical slab thickness, which depends on ambient temperature, thermal conductivity, convective heat transfer properties, reaction kinetic parameters, such as the heat of reaction, activation energy, and pre-exponential factor. Once the physical, kinetic, and heat transfer data are known, the critical thickness can be computed. Only slabs with thickness less than the critical value will be safe from spontaneous ignition under the given environmental and kinetic conditions. As noted earlier, to prevent spontaneous combustion, the delta factor must remain smaller than the first eigenvalue. Under this condition, the temperature distribution in the coal slab reaches a stable steady state. Because delta is below the first eigenvalue, both the numerator and denominator of the governing function remain positive. The maximum temperature occurs at the center of the slab. This is also the point where spontaneous combustion would initiate. The dimensionless central or core temperature depends on 3 key parameters: gamma, beta, and the Biot number. A plot of dimensionless core temperature versus the slab's dimensionless thickness shows that the center temperature increases gradually at first. However, as the slab approaches its critical thickness, the temperature rise accelerates rapidly and moves toward the ignition point. This rapid increase near the critical thickness represents the primary hazard that must be avoided. In this analysis, the coal sample is modeled as a flat slab. What result would be obtained for the critical radius if the coal were assumed to be spherical? With the hope that by raising this issue, we can recognize the value of mathematical modeling in preventing the catastrophic consequences of such processes.